Hi, I'm Girish. I have chosen the paper titled One Tokenizer to Rule Them All, that is the Universal Tokenizer. This screenshot is taken from the video where the author explains their paper. This was posted on the Cohere's YouTube channel. In this video, they mention that when a tokenizer hasn't seen a certain language before, it often breaks the text into more tokens than it would for English. That's because the segmentation isn't as clean or accurate. But in the paper, they have used a compression ratio as the main metric to measure this. That basically measures how efficiently the tokenizer stores the text in bytes. So it's talking more about the storage space rather than the number of tokens. Let's say hypothetically English were a low resource language, the world unbelievably might have split into more tokens. So in this case, it has split into three tokens. Even if the compression ratio is low for this, which seems good according to the paper result, high fertility still signals a problem. So a lower compression ratio alone does not guarantee that the tokenizer is truly effective. It may still fail to represent the language efficiently. So I think the better metric would be the fertility score because this tells you how many tokens the tokenizer produces per word or sentence or a character based on how you define it. So this matters more because in real world application and most researchers and companies care more about keeping the tokens count low than saving few bytes. That's because the cost of running LLMs increases with the number of tokens. In the second slide, I would like to explore a new architecture. So according to paper as shown in the previous slide, the tokenizer tends to assign more tokens to unseen languages. However, several studies have shown that this issue persists even in models like GPT-4, even for included languages. As it has been observed that the GPT-4 tokenizer has 4x fidelity penalty in Korean and Hindi compared to English due to frequency bias in training data. Since English language dominates more, so the byte pair encoding merges are optimized more for English and Latin related languages. So a promising solution is additive merging tokenizer. So it keeps the original tokenizer as it is. So in this case, it's the English plus Latin script tokenizer. Then a new tokenizer is trained on a target language. So it could be Hindi or Persian, etc. Then merge the new tokens generated from that new tokenizer into the existing vocabulary. So this allows the language specific optimization without retraining the entire model, and you don't need to commit to a specific languages early in the development of tokenizer. Although this increases the vocabulary size, universal tokenizer also requires a large vocabulary, as explained in the paper. So the comparisons remain still fair. There are certain solutions that could be explored. Is the clustering of tokenizer by script similarity, example Latin and Devanagari, is more accurate than the regional groupings like Middle Eastern Indic, which was used in paper, where they combine languages like Persian, Hindi, and Vietnamese, despite using the different scripts like Arabic, Devanagari, and Latin. So, since the paper attempts to use regional clustering, we can use a script-based grouping or vocab tuning to reduce the number of tokens in the vocabulary. In the last slide, I would like to explore one more architecture. So in this research, we explore a multi-tokenizer architecture where each language has its own tokenizer, embedding and unembedding layers as well, while sharing a common stack of attention and MLP layers. So during the training time, as you can see in this flow chart, we tag each piece of training data with the language identification special token called lang ID, like EN for English and HI for Hindi, etc. And then train the model to recognize and process the lang ID tokens, which ensures that the model learns the lang ID token act as a clear switch, telling the MLP and attention layer that this is an English sentence, so route it through English head. Or if it's a Hindi, so route it through Hindi head, etc. So at the inference, as you can see in this flowchart, the input text first passes through the language identification algorithm, then this algorithm appends the correct lang ID token, then trains the text to appropriate language tokenizer before feeding it to the model for generation. So all these models can be used for evaluation through certain metrics such as fertility score, model quality, where we can use the win rate percentage itself as done in the paper. We can also check for inference speed and cost. I hope you find my suggestion insightful. Thank you.